So my name is Etienne, and I'm working at Wolfram in the domain of machine learning. And so I will present you today the function we worked on for roughly the past 2 years. And then I will tell you a bit about what we are currently working on, and also what's our project for longer term. And so I think it's a good occasion that you ask questions and give your comments about what we did and about what we want to do. Maybe you say, no, this is stupid, you should do that, because in my work I really need that. So that will be useful to have this feedback. All right, so quickly, I'm going to define what I mean when I talk about machine learning. So, very broadly, machine learning is when a computer learns a model from data. So it can be a very stupid thing. Actually, you could argue that computing the mean of a list of values is already machine learning. So it can be simple models. For example, fitting a curve. You have some data. You want to find a y as a function of x. This is this mapping. This is machine learning. But it can also be more complex. For example, in the case where you want to classify image, whether they are cats or dogs, you will need to fit a model that is much bigger, such as a deep neural network. In practice, actually much bigger than this representation. And we usually classify this machine learning in 3 learning types, roughly. One that is supervised learning, which is the most classic one. It's learning a mapping from input to output, as function of data, trying to predict an output that can be canonical values, numerical values, other type of things. There's also the domain of unsupervised learning, where there's no input-output, there's just data. So you can see that as only inputs or only outputs, actually. And you want to learn the structure of the data, whether it is a distribution of the data or just some statistical property or just something interesting about the data. This is the domain of unsupervised learning. And a third domain that is a bit less known, about reinforcement learning, which is really about how an agent in an environment that has feedback from this environment is going to learn how to behave in this environment. So you can imagine it's for robots and things like that. And so typical task of machine learning, just to give you an idea. So image recognition, sound recognition, text, classification, prediction of a variable in data set. So here you have data set of people, you have their age, their gender, and you try to predict their height. Predict the future of a time series. Text translation, imputing missing values in a data set. In the case, just for illustration, took the problem of an image. Detecting anomalies, clustering data, compression as well, can be done efficiently with machine learning. As I talked about, robot learning how to move. And also data mining tasks, where it's not a computer, you don't teach a computer to do a specific task. You more ask the computer to model the data, and in the hope that it will give you insight about this data. So it's more computer to human type of task. So for example, one way to do it is that you look at the model, that result, and you say, oh, okay, I understand. My data is like this, is like that, and then a human can take decisions. So that's another task. But the techniques for data mining and machine learning are pretty, closely related. All right, so as I told you, I will first talk about what we currently have in the Wolfram language. And so when we talk about machine learning function in Wolfram language, there's actually 2 types of functions. They're the functions that allows you to do machine learning yourself, so to do learning yourself with your data, such as classify and predict, find distribution, dimension reduce. I will talk about these. And also some function that we coded using machine learning ourselves. So kind of built-in machine learning or built-in models. That's sometimes we call it that way. And probably the most famous is image identify that you have seen at the keynote yesterday, probably. And so I will talk about both of them, and then I will talk about current project and what we are going to do in the future. All right, so first, so classify and predict. So they are the most classic function for machine learning. That was the first function since version 10. And to do, so yeah, the most usual task in machine learning, which is supervised learning, so learning a mapping from input to output. In that case, the input can be very various type. It can be just data, numerical data, categorical data, a mix of both, image, text, and sound, and a mix of all that. And it should work. Of course, you can not really throw anything at it, but it's quite varied. And the goal is that you can throw anything at it. On the other hand, the output is quite restricted. It can either be a numerical value, like in the case when you predict how tall is someone as a function of some features. So in that case, a numerical value, I did it reverse, it would be the function predict. Or it could be a categorical value, A, B, C, that we call a class, and then you would use the function classify. And what's important about these functions is that we design them to be very high level, very automatic. So that's if someone doesn't know the machine learning algorithms or the machine learning procedure or good practice, they can still use this function. So I'm going to show quickly about it because I want to talk about these other functions. And many people complain that the talk I gave last year was the same as the talk I gave this year. So, okay, for example, here we have a data set. So you have a list of examples here with a rule. On the left of the rule, you have the features. I mean, you have the input. And on the right of the rule, you have the output. So here it's learning to classify pictures of written digits to identify what digit they are in. So I run classify on this list. It outputs a classifier function. So here it's a tiny data set. So that's why it's quite fast, but the performance won't be great. And then this classifier function, you can use it on some new function. So I don't know, we could use, we use the 8. Let's see what it gives. So okay, the 8 is correctly classified. You can also ask for the probabilities. Or let's here ask just the top probabilities. So this says, I believe, according to my data, according to my model, that there's 64% of chance that it's 8, 20% of chance that it's a 2, and a small amount of chance that it's a 1. And okay, so predict is very similar. Here I again show an image because it's nice to visualize. And here I will associate numerical value to this image, which actually is the area of the colored part. And it outputs a predictor function, and this predictor function, I can again use it. So I don't know, I can use this one. So this one will tell me it's 20. Actually, I don't, oh yeah, this I guess you cannot do by, I guess your brain will have a hard time actually computing the area contrary to the thing. But it's actually very accurate, but this task is pretty easy for predict. And you can also ask the probabilities. So here, since it's a continuous value, it's not probabilities, but continuous distribution. So here it says that my belief for the output for this input is a normal distribution centered around 7.1 with a tiny standard deviation. So I mean, it's clear that this for this problem, predict is quite precise. Yes. So here it's always symbolic distribution that we have in the language. Yeah. It will. Yeah, when we generalize predict to any type of output, it's going to be more complicated because something that output a text, what is the distribution in the space of strings, of text, it might be something harder. So we'll have the problem later. Yeah, sometimes it can give a histogram. So yeah, a distribution histogram. Like there's a built-in predictor name age where you give your name and it tells you how old you are. Obviously, it's mostly wrong, but you can have the distribution, and it gives its belief of your age given and it's a histogram, given your name. Okay, more about, put here some example of complete machine learning project. And there's a workshop we'll give with Sebastian Bonenstein Thursday about building smart applications that learn that will use classify and predict a lot. Okay, and of course documentation and all the usual tool to learn that the language has. So now I will talk about a different type of a function. So it's still learning functions, except that here the goal is not to have the function that is, the machine learning model that is as good as possible. Here it's more to have a model that is interpretable, that you can understand. And it can be useful for many things, for scientific research, for example. So for example, find formula. The principle is very simple, is that I have xy points, okay? And I try to find a curve fitting these points, but not just a curve like a black box function. I want actually something with a mathematical formula. So I do find formula. And so this is an interesting algorithm that does that you should actually, I can tell you right now, you should go to the talk of Georgia Fortuna Thursday at 1 p.m. where she designed this function, and she will talk a bit about what's underneath. It's some cool Monte Carlo things going on. And here you can plot the function with the data, so it actually found the function in that case. There's also fine distribution. I won't talk about it, but it's the same, but to find a distribution. So let's say you have a unidimensional distribution, a mixture of two things. You want to find, is there a simple symbolic distribution that fits this data? So now we'll talk about dimensionality reduction. So it's not supervised learning anymore. There's no input-output. The goal of dimensionality reduction is to so let's say you have a data set of numerical values, okay, a bunch of vectors. Each vectors have a given dimension. The goal is to map these vectors to another vector in a lower dimension. And but while preserving information, so it's a sort of compression with some other properties. The idea is that in this reduced space, it will be much easier to do all sorts of tasks you want to do afterward. So there's two functions. One is called dimension reduce, that actually reduce the vectors, and one is called dimension reduction, that produce a dimension reducer function in the same way as predict and classify do, and that you can use later on to reduce data. So I'm going to show a quick example. Probably one of its main use is for visualization. So here I have a data set, and where the input is a bunch of vectors of dimension 4. And I want to visualize these vectors in 2D. So what I do is that I apply dimension reduce to all these vectors. And you see here that it's vectors in dimension 2. And I can now visualize. So here it was so the labels of these vectors, but this time in dimension 2. Okay. There's another application that I like. It's about doing data imputation, so imputing missing value of a data set. So I'm not going to detail because there's other things I want to talk about. And but roughly, I'm loading the data set of unwritten digit, the same as we used before. I'm taking the data out of this image. I'm doing a big vector of this image, and I'm also shuffling it. And in the end, you have a dimension. You have 10,000 vectors, dimension 784. I cut that into a training set and a test set. I create a dimension reducer that reduces the vector to dimension 50. Okay, and what's interesting about that is that when you put a vector in this space with a 50 dimension, there's some sort of understanding of how should I put that? Okay, let's show instead. Like this model is an unsupervised learning model, and there's a sort of understanding of the statistical structure of the data set. And that would be useful to do image completion. So here I take a random vector. You see this is the random vector that I chose. And I'm reducing this vector. So you see now I'll just have 50 dimensions for these things. And if you use, OK, and now I will take so this vector, and I will remove some pixels. I will put missing values instead of these pixels. And this is just to visualize it. And I will use this dimension reducer with the property imputed vectors, and so applied on the vector that has missing values, and it will reconstruct the missing values given the model that it has of the data. And I hope it's not too bad. OK, it's something. This is the original image. This is the image with the missing values, and this is the imputed image. So of course, I mean, for image, you should use the impate function that is in Mathematica instead. But what's nice is that you can apply that to any data set. So if you have a data set, you try and dimension reduce, and then you'll be able to do missing imputation later. Yes. So yeah, I mean, impate is not learned on your data set. Yeah, so yeah, it has another advantage that you have just one image. You want to impate it, you just give it to impate, it works. where this is learning an inpainter, so to speak, with your data. Okay, now let's switch to from function that you can use to learn to function that we did some machine learning to create these functions. So the most famous is probably image identify, which I won't talk much because, again, you should go to the talk of Sebastian Bodenstein. It's also Thursday at 11 a.m. There's a lot of talk Thursday. You should be there. A shallow tour of deep learning where he'll explain in detail what he did for image identify. It's the one that coded these functions. And also how you can do, will be able to do image identifier in the future yourself with your own data. And but to speak briefly, it's something that uses a deep convolutional neural network that has been trained for a month on GPUs, although now it's quite faster to train. And it's trained of 10 millions of images, which is a huge amount of image if you think about it. Like if you try to think how much a 1 year old has seen image in his life, telling that when the images are too similar, you don't count them as the same, because it's correlation. So if you say each 10 seconds you have a new image, we should compute it. We don't have time, but it's probably something that is not too far. Okay, so it's about 3 years of image. It's a lot of data, and that's one of the reasons why we managed to do image identification now. And I can resist to show something. I will do current image. How does that work? Okay, just to take an image of myself. Okay, good. And and we can try image identify here. All right, so I'm a person. That's good. And okay, I have a bit of problem in the entity representation. That should be a nice orange box. But and one thing you can try, and it's always fun to try. It's another thing that Sebastian did as well. It's to recognize famous persons. But sorry, I don't know what to write. Notable person, right? This is English. Okay. And and of course I'm not in this data set, so it just tell me which famous person is the closest to me. And Manny Pacquiao. I guess on this image with a cat, yeah, okay. Boxer. It's very fast. It's much shorter, but yeah. Okay, and so go to Sebastian. He will tell you all about that. It's fascinating. And okay, some other things we did about natural language processing. So a bunch of built-in classifiers. So things like language identify that you can also call by doing classify language and second argument things. And okay, it's English and yeah. Oh, you do on current image. That's quite nice to do. With dynamic, yeah, it's very nice. You have to ask Sebastian to do it. And okay, this is kind of a classic but quite useful function. Something to detect a topic, but restricted to Facebook topic actually. We are planning on we'll talk about it on doing a more generic one. And text cases that is quite recent. It was in 10.2, and that I call the natural language processing Swiss Army knife because you can do a lot of things with it. And so, for example, you can cut things into sentence, which is a task that is not that trivial because you have a lot of cases, where Mrs. Fox with a dot, and you might try, you might think that that's actually the end of a sentence. So it has been learned with machine learning, and you can ask, for example, I don't know, all the noun in this sentence. And so John and Mary, okay, store and table seems to be the noun. You can ask, okay, give me all the country of this sentence, and you can. So it doesn't just return the value. You can also ask it to return the position, things like this. So you can do some cool things. For example, let's say, yeah, I want all the English sentence. Okay, so I don't know. Okay, I don't know. My Spanish is very limited, so as well, I think it's good, right? And English again. Okay, so here it should extract all the English sentence. But I can also ask, English and give me the positions. So here it position, I guess. Okay, it will give me the position in the string where they have English. You can also have both. So I want to have the position. Actually, let's look at the documentation. So it is the form, string position, type. Oh, type is good. So I will type position. So it will be English. It will tell me English is there, English is there. And then I can add other ones. So let's do English and then Spanish. Okay, it will tell me there's an English sentence between these two positions, another one between these two positions, and a Spanish sentence between these two positions. So that's a thing that can be quite useful when you treat with a lot of text. And a function we did very recently, text structure, which is about visualizing the grammatical structure of a sentence. So here you have a parse tree of the house is blue with a part of speech here and the phrase type around it. And you can also ask, for example, just part of speech, and it just gives you the part of speech. It's to visualize, but you can actually, if you look at the input form of this, it's a bunch of nested text elements, and you can also do computation with it. But I must say that to do computation, text cases is usually easier. All right, so I'm finished about what's now in the language, and I will talk a bit what we're more excited about us, meaning what we're currently working on. And so one thing, and by the way, yeah, don't hesitate to ask questions. And it's also the last talk, so I guess we can take questions. So I mean, don't hesitate if you have any question about what I just talked about. You don't have to wait for the end. So there's a bunch of functions that we want to do that use deep learning because we acquire knowledge on how to train these deep neural networks. So now we want to use that. We want to leverage that to train other things that image identify. So we want to do some specialized, we are doing specialized image classifier. Currently, we're working on speech recognition. So there's probably a function that will be called speech to text, I guess. I hope soon. On image cases as well. You can ask Sebastian about that again. Which is the goal is not only to recognize what's in the image, but also recognize all the elements that are in the image and tell where they are. Okay, like in this example. And then again, leverage this understanding of deep learning to provide a framework that you can use to train this deep neural network, and which is a big project because it's not tiny models. It handles a lot of data. So usually it uses GPU training to be faster. So it will allow to train the model either on CPU or GPU. And with a bit of luck, it should be in 11. If you ask Steven, he will say for sure it will be in version 11. Probably. Okay, there's also some work on unsupervised learning. So I told about dimension reduce. That was a function for unsupervised learning. But there's a bunch of other functions we want to do that correspond to typical tasks that people are doing. For example, cluster classify. So we already have clustering function in Mathematica. This one will return a classifier function. So it will first do a clustering and then output a classifier function. So if you give a new data, it will classify the data according to these clusters. And also this function, to be automatic, so a bit similar to predict and classify. Feature extract, which is something that kind of an extension to dimension reduce, except that it's not about only numerical data. You can input anything at it, and it just output a nice vector that represents what this data is, compressed but preserving like semantic information, okay, in a way. And anomaly detection, imputing missing data, density estimation, error correction. So I won't talk much about it, but it's things that we are working right now. So one thing that I want to talk a bit about it, I'm quite excited about that, it's Bayesian optimization. It's actually Piyush Kumar that is working on that. He's a new employee, if you want to talk with him. and that I call sometimes model-based optimization. So it's when you're optimizing a function and you're in the case where this function is very slow to evaluate. So let's say you are trying to find where there is most oil in a geographic area, and then you do a drill, and you measure how much oil there is, and then you do another drill and you measure, but you have a lot of course, each drill takes maybe 1 week to do, so you have a lot of time to think. Given that I have 1 year of exploration, where should I do the next drill? And so to do that, what you do is that you use a model that is very good on small data. So this is not big data at all. It's when you have 3, 4 points. It's tiny data, but a model that is very good on tiny data, and to fit the amount of oil given the data you have. And this fit should have, so inside of it, what's your guess about the amount of oil, but also the error bars. This is very important. And that's why it's called Bayesian optimization, because it's very important to have a probabilistic model there. And then given this model, so here you have an example. You have your 2 data points. In dashed, it's a true function. In black, it's your model. And in purple, it's your uncertainty. And from that, you can figure out, OK, I should probably look there. And usually you look at a place that you think it's quite high, but there's also some uncertainty. Because if you drill just next to where you drilled before, you don't learn more information, even though you have a high chance to have something high. But in that case, but that would be a bit useless. So, and then another thing we're working on is on text functions. So text cases, we want to drastically improve it because there's many things missing. Like if you, eventually text cases, you should be able to ask anything you want. Like, give me the street address, give me the, I don't know, anything you can imagine. Should be able to ask street cases, so text cases. So we are working on it. Generic topic identification. In the same way as image identify, we should have topic identify. And language translation. That is something that we are working on as well. OK, so that's all for what we're currently working on. And now we'll talk about our future project. And that we're also quite excited about, but didn't start it yet, unfortunately. One is about extending predict to handle any type of output. Because so far, right, it was just either numerical data or categorical data that you can predict. And you won't be able to predict a vector of categorical data, a vector of categorical data, and numerical data together. Anything, sequence, text, even image, why not? Predict an image. That would be maybe a bit weird, but that sounds weird, but it's actually a type that might happen. And any combination of this output type. So that's something we want to do. We want to work on probabilistic graphical model, which is a bit at the opposite of our philosophy, not our previous philosophy, but predicting classifiers, the philosophy of this function is to be as automatic as possible and completely black box, where the user don't have to care about anything. And it's quite hard with predicting classify to if you have knowledge yourself, like expert knowledge about the problem you're doing, to actually put some information there. You can select the model with a method, some parameters, but it's not the greatest. The best for that is to use graphical models. It's something that is used a lot in medicine when they already have a lot of expertise. And you would, so it's kind of a language to define a model. And so you define this model with this language, and then you have data, and the parameters of this model are learned. And something that is even, even more generic is probabilistic programming, which also is defining a language that defines probabilistic models, and something that is more generic than graphical model. Graphical model is a bit restricted, although it's already very useful. So that's something we are working on. We want to work on. And automatic data analysis. So something where you give data, and a bit like find formula, it would feed the data in an interpretable way, and then it would give a report about what this data, what this data analyst found in this data. There's some nice example of in research group that's motivating us to do that. And we want to work, natural language processing, text summarization, topic modeling, but in an unsupervised way, fact extraction. And then there's some other learning types, such as active learning, which is when you do, for example, a classifier, but your data is not annotated, like you have a bunch of cat and dogs, and you have an oracle that can tell you which, if you give it an image, it tells you, this is the cat, or this is the dog. And so the program has to be smart enough to give the oracle the example that will make him get as much information as possible. And that's very useful for curation tasks. For example, for image identify, you could have the program that is building image identifier that asks the curators, what is this image? I can't recognize it. So it's actually something that asks questions and that learns through asking these questions. And reinforcement learning, that is a really interesting topic, which is a bit similar to active learning. It's a robot that needs to learn how to walk. And again, it's kind of asking a question. It's asking a question to the environment. What happened if I put my leg here? Is it better? And there's always this trade-off of trying to explore, so trying to do a movement that you have never done before to see if it works or not, and to exploit what you already know. Because you know that the solution is probably next to what you have already. And finally, it's something that many people ask for, but it's something that is not easy. It's scalability and deployments. It means that most of our algorithm only use a CPU, and the neural network will use GPU, and we want to have all our algorithms using GPU. And that's something that we have to do an effort on. Also, when you have too much data that cannot fit into your memory, it should be able to have some kind of online algorithm that look at data chunk by chunk. That's something we want to work on. And finally, and this, I don't know, might be quite hard, but I think we should have a look at that, is manage to export models to other language. Because for now, you can already use in your language through an API. So you do a classifier function, a predictor function, or something else. You deploy that to the cloud in an API function, and then you can call this API through any program. So you can already use it in any project. But for some people that, I don't know, have a robot that is there and that cannot be connected to internet, they might want to have the program actually locally, and because the project is not in the Wolfram language, they want to convert this model to their language. And fortunately, of course, as you might expect, there's some problematic here because our models do much more than just do the prediction. They do missing imputation. They do all kinds of things that are hard to translate to a language, but that's something we're going to try to do, I think.